today's seminar we'll be talking about fatigue analysis using SolidWorks Simulation Standard feature. The objectives, we're going for fatigue definition and stages of the fatigue. We're introducing fatigue analysis types and also the loading types. Then be emphasizing on just constant amplitude fatigue terminology in SolidWorks, and also be adding the important feature of fatigue studies, which is called stress-life or SN curves definition, how we get the data and the interpolation schemes. We will emphasize on mean stress correction methods available in SolidWorks simulation, and then we accomplish our session with a case study, which is a fatigue analysis of a pressure vessel. We will go over how we define SN curves, how we define events in fatigue study, and also study properties. And in the results section, we will review the damage plots. All right, now let's start with fatigue definition. Fatigue is the weakening of the material caused by repeatedly applied loads over time, even when the induced stresses are considerably less than the allowable stress limit. Simply means when you're repeating a load, you're taking a life out of that, let's say, component. And this repetition depends on the level of the stress can reduce the life. Most of the designer, they consider ultimate strengths for their components and they design for strengths. That is good if we have just one loading scenario. But in real life, as all of our loads are cyclic or variable, then instead of having just design for strengths, we have to consider fatigue and we have to design for life. And there are so many examples around us. Well, a very, let's say, highlighted case was happening in the airline, Aloha airline, and the, let's say, body structure of the airplane were designed for 75,000 landings. And actually, it's happened to be exploded suddenly because it was more than 75, and it's reached to 85,000 landing cycles. Well, that could be really life-threatening in so many applications, and that is something we always have to consider when you're providing a warranty to your, let's say, products, and also preparing the, let's say, maintenance instructions. All right, let's have a closer look to stages of the fatigue. We have major 3 stages. The first thing is happening in areas where high stress fluctuations, such as notch or in a scratch or in a, let's say, internal defect, you will develop, it will be developed some, let's say, few cracks, and that is going on a very macroscopic, let's say, scale, and it's not recognizable by eyes. And as the stress and loadings are getting repeated, some or all these cracks will grow and result on something obvious and recognizable. And then in stage 3, the ability of the material to withstand the loads continue to deteriorate and the failure will occur. Basically, what is very important to make your, let's say, product to be more equipped with the fatigue, let's say, failure is make sure there is appropriate coating and as much as possible to avoid any imperfection in your manufacturing. That is the first, let's say, step you can take to make a weather guarantee. Now we come to a very important slide here. We'll be talking about fatigue analysis types. Based on the stress magnitudes and the number of cycles we need to cause the damage, fatigue can be divided into 2 basic groups. First is low cycle. In a low cycle, we have alternating stress which have higher magnitude, and it is causing significant plastic deformation. In those type of fatigue studies, the structure fails definitely, and it has considerable plastic, let's say, deformation. The appropriate approach for those sort of a study is strain-life approach, which is not part of SolidWorks fatigue code. However, in other situations, if our alternating stress magnitudes are moderate to cause none or small levels of plastic deformations in the material, the appropriate approach is stress-life approach, and it's called high cycle. This is what we can consider and simulate in SolidWorks simulation. Well, as you can see, stress-life is, which we can call it SN, requires some input data which is called SN curve, and this is what we are going to introduce in the next slide. But the main highlight is here in SolidWorks simulation we are able to let's say simulate high cycle fatigues, and the level of stress is near the failure or even less than this. There is no significant plastic deformation on the structure. And what we are concerning real is if these stress levels are getting repeated and repeated, and what is the outcome of the study. All right, now as we know, we're talking about fatigue, and it is directly connected to the loading, a load which is getting repeated. Various loading history we can have, but mainly we can, let's say, divide it in two main groups. One is a constant amplitude loading, so it's getting, let's say, from a plus to a minus, and with the same amplitude is getting repeated. Or it could be from plus to zero. That is not the main concern, but the main thing is the variation has a constant amplitude. And the other one, well, we can't really having any specification or making any trend to our variable, to our loading variation, as what you can see in the picture. So it's variable amplitude loading. Both of these loading history can be considered in SolidWorks simulation and fatigue studies. Well, today, let's say, case study will just consider the constant amplitude loading, and variable amplitude loading examples and webinars is coming in our next scheduled webinars. Okay, now let's have a closer look to the amplitude loading, constant amplitude loading terminology. If we have a look to this stress variation over the time, we can see the first thing is Smax and Smin, which is maximum and minimum stress magnitude in a stress cycle. We have alternating stress. We have mean stress, which is an average between, let's say, maximum and minimum stress. And also we have the stress ratio, which is Smin over Smax. Now, this general presentation of constant amplitude loading history could be more specific if, for example, the stress ratio is 0 and S-mean is more than 0. That is called zero base. Or basically, we have top stress plus, minus stress 0. That is one type of stress fluctuations we might have. And the other type is fully reverse, where you can see the mean stress is sticking to nearly 0 value, peak stress is plus, and minimum stress is a -1. And that is more critical if it's happening into our, let's say, design studies. That simply means we have compressive and tensile loads acting on the component will significantly reduce the life of our design. So mostly we are concerning about this one as a hypothetic sort of stress fluctuation if it's happening. All right, we mentioned that in a high cycle fatigue studies, okay, we need the SN curve, and the approach is stress-life approach. Well, you can see a sample of SN curve on this picture. Well, it is a correlation between number of cycles to failure, which is called N, at different alternating stress level, which is S alt. So we can see fatigue stress alternation and number of cycles to cause the fatigue. You might have a different scatter points when you are really testing, and the next scheme is to obtain that and make a data interpolation scheme fitted to those, let's say, points. One thing we have to, let's say, introduce here in SN curve, there would be a value of alternating stress, the highest values of alternating stress. Well, the structure will have infinite life, or there is no fatigue will happen there. This is called endurance limit, and we have to consider, and that is something we have to know. Some material may have it and some may not. And basically in the figure you can see if you are in this area, then the number of cycle is 10 to the 5, and if we are going to the lower stress, we have more life to repeat the load. This data, as we said, could be from several test specimens subject to the cyclic loading until their failure, and they record this data. And since the data is being obtained, then we have to make a test data interpolation scheme and prepare a graph. Now in the next slide, we are going to introduce that. The first scheme we have is logarithmic or log-log, let's say, interpolation scheme, and just mentioning it's based on 10 for both alternating stress and number of cycle. So let's have an example and introduce and explain it better. Imagine if we have a test data for a number of cycles 1000 at alternating stress of 50, let's say 1000 psi, and also we have alternating stress of 40,000, and the number of cycle is 100,000 cycles. Now we would like to know what is the number of cycles on 45,000 psi. If you're using logarithmic scale for this data interpolation, what would be happen? On logarithm s-axis, then you get these values, and you get the logarithm on number of cycle and put it 3 and 5 here as well. Then within a linear interpolation, you will specify your alternating stress logarithm of 45,000, and you will get the let's say corresponding value of number of cycles. This method of log-log could be used when you have a few data points and they are widely scattered. Now the other scheme we can sign on a method of interpolation is linear interpolation for alternating stress, and logarithmic interpolation for number of cycle, and this is called semi-log. Well, obviously we're using alternating stress as they are, and we're getting the logarithm of number of cycles on the other axis. So we can use this method when a small stress range compared to the variation of number of cycle. And the last one would be a linear interpolation for both alternating stress and number of cycles. Well, if you have many data points, we're simply using this method, and we simply preparing SN curve, which is representing the real values of alternating stress and number of cycles. So you conducted a test on your actual product or actual material, you got the data test, and this is simply a correlation between alternating stress and the number of cycles to cause a failure. Now it's your turn to enter that data in SolidWorks, let's say SN curve section, and tell how these two set of data is correlated: logarithmic, semi-logarithmic, or linear scale. Okay. Now the next question is, all right, it's not always possible to have, let's say, a fatigue test data beforehand and get the SN curve. Is there any alternative, let's say, method? Well, definitely, if you are providing any SN curve from the reality test data, either you do it yourself or finding on a, let's say, open literature, that is perfect. However, if we have no fatigue data and we're using authentic or carbon steel material, based on the ASME code, we can drive the, let's say, fatigue data based on material elastic modulus. What is happening in SolidWorks, let's say, SN curve data entry, you will have the option to drive this from material elastic modulus either based on authentic, let's say, steel curves or carbon steel curves. And what is happening? The alternative stress of selected material will be calculated at each level by multiplying the sample data from ASME to the ratio of elastic modulus of selected material to ASME material. That is a shift to values of alternating stress of standard, let's say, material of ASME code to based on the elastic modulus and get a shift to the alternating stress values. So this option is available if you have no fatigue data. It could be used very carefully, and you have to review all these let's say data curve very cautiously and make sure it is fitting to your let's say material, and your material can be fitted on these two categories. Otherwise we're predicting a very wrong result, and it might come with a very bad evaluation about the fatigue life and the warranty you might let's say provide. Now, the other important issue we have here, and we have to, let's say, explain that one, is the importance of, let's say, mean stress and the correction method in predicting, in presenting the SN curves. The first thing I have to mention is the mean stress has a very, very significant impact on fatigue resistance of the material. Well, as we said, if you have zero base, means your mean stress is positive. You're just having a tensile load on your, let's say, structure. Well, that could be different, let's say, life if your load is getting, let's say, fully reversed, or your mean stress is zero. You have plus and minus, or let's say tensile and compressive. That is two different life story. Therefore, we are again emphasizing the mean stress has a very significant impact in resistance of the material to the fatigue. Therefore, what is also very important to understand when you, let's say, doing a study and you're getting the stress distribution, you can see there are different spots with a different or variety of minimum and maximum stress values. That is also means our mean stress can fluctuate within the same model. That is requiring to have different SN curve for different values of mean stress within the same part. This is an opportunity again in SolidWorks. You can have up to 10 SN curves for a different mean stress values and enter it to SolidWorks and make your studies more and more accurate to predict the fatigue. However, in most of the cases, this is not feasible to have, and based on the theory, we can consider the mean stress influence by three methods. The first one is the Goodman, and it's recommended for brittle material. Second is Graeber, which is experimentally good for ductile material. And the third one is Soderberg's, and it is yields conservative result in tension. Now, as you can see in this figure and the graph, the correction factor is correlated to the values of alternating stress, where we can see the horizontal axis represent the magnitude of mean stress, S mean scaled by the value of material ultimate tensile strength. Here it is, S mean over S ultimate. And also the vertical axis shows the corresponding correction for the fatigue stress of the material which is S fatigue, corresponding to fully reversed or R-1 SN curve. So we can see these two correlation here, and this is what we have available in SolidWorks. Well, the only thing you have to do is to understand which one is fitting to your material type, select them, and simply give it a correct, let's say, values for considering the mean, let's say, stress influence on your study. Okay, so that is all we have to introduce about fatigue. We mentioned what fatigue means, how it is going to act, what is the basic terminology. We emphasize on low, let's say, cycle and high cycle fatigue. Well, we are considering high cycle fatigue in SolidWorks. We introduced the loading story with constant amplitude or, let's say, variable amplitude. And be mentioning that the case study we will take today is talking about just a constant amplitude, and we introduce the SN curves and also the effect of mean stress and interpolation data scheme. Now, the case study today is talking about an aluminum alloy pressure vessel which is undergo to evaluation of fatigue life of constant amplitude pressure and thermal stress loading. Well, you can see in a picture, this is the pressure vessel. For simplicity, we are simply scale it down to 1/10 of the whole, let's say, component, as it's fully symmetrical. Our pressure load oscillates between minus 0.66 megapascal to 3.3 megapascal. Heat flux oscillates between 0 to 1471 watt per meter square, and we always have a dead load of 66,725 Newton on top of the lid. What we would like to see if there is any fatigue occurring after 2 million cycle of thermal loads and 500,000 cycle of pressure load. Okay, so the case will consider the symmetrical condition with a dead load, variation of pressure, variation of heat flux. Well, that is simply end up with the thermal stress and always having a dead load. All right. Before I go to the case study, let's draw a very good illustration about what we are going to do and what is required to be do. So basically, stage zone analysis and loading events. Well, we said fatigue study is the repetition of load or, let's say, alternating stress. Therefore, in any fatigue study, we need some event. That simply event is defined by an alternating and mean stress levels and number of cycles in fatigue study, which can refer to one specific static or multiple static studies. You're simply telling the software there is an study with the values of stress, and it's going to be alternate. Okay, so for that reason, you need to define an event in your fatigue study which is fully linked to the values of stress from series of linear static, and in 2016 you can have dynamic studies added as well. Well, back to our case study, we mentioned we need to have a linear static study where we have a pressure load and a dead load of 3.3 megapascal and dead load of scale of 110 on a top lid. Similarly, we have another pressure load linear static study. Well, this time we have minus 0.66 megapascal and a dead load. So the first event will consider the variation of your stress from what you have at the maximum pressure and what you have as a minimum pressure. And it's defined by a loading ratio of minus 0.2 for 500,000 cycle. Similarly, when you have a thermal study of heat flux maximum 1471.8 watt per meter square and a dead load, this will end up with the thermal stress study. That is the first value. And second, when you have no thermal stress and you just have a dead load. This alteration between 0 and maximum heat flux, or let's say 0 and maximum thermal stress, should be repeated by 2 million cycles, and obviously it's from 0 heat flux to maximum heat flux. Therefore, our second event is a 0 pace. All right, so what we have to, let's say, prepare is first have the heat flux and make sure we're doing a thermal stress based on that heat flux. We have a linear static study with minus and plus pressure loads, get all the stress values calculated, then prepare a fatigue study where our events are using or referring to those variations. Okay. Before I open up the model for you guys, one thing I have to, let's say, mention here. Well, when you have multiple events, you have the option to say how these events are interacting. The first option is no interaction. Simply, all events are sequentially happening after each other. That is one option, and you will get a different result. The other option is random interaction, means simply you letting the software to go over the possibility of mixing the stress peaks from different events. So both of these studies is what I will, let's say, set up, and we will look at the result value. All right, so let me bring up the model and we have a review. Well, we said this is the pressure vessel, and you can see it here. And it's been symmetrically cut. The first thing I have to do is to make sure I'm applying my, let's say, heat flux to a thermal study. Here is the thermal. Well, you can see this is the material first. Contact set between the material is we have a thermal resistance between top lead and bottom. Look like we have an isolator or gasket between those things. Convection is set to this value on outer faces, and also, as we said, there is a heat flux from inside all these faces with the value as the maximum you can see here. Based on this, we have applied some mesh controls on an appropriate area. Well, we are expecting some stress concentration like the bolt here, and then we simply started our study and we got the temperature distribution, as you can see. Well, one thing I have to emphasize beforehand, guys, thermal studies outcome is temperature distribution. Well, because of the temperature variation on an assembly and different components, as they are expanding differently, then we might experience thermal stress. So do not mix up one very important thing. Thermal studies are thermal, let's say, class of material, class of, let's say, simulations. But thermal stress is structural, means your load is not force, your load is not pressure, or etc. Your load is temperature. And this is exactly what happened next. In a thermal stress study, I have set up my structural or linear static study with the same material and a connection which is a bolt connector between these two faces and a contact set of no penetration between top lead and the bottom, and simply fixing my model on various location, such as this one cannot move normal to its face, and also there is another restraint of here, a symmetry applied on this one as we have cut it, and also the other restraint as the symmetry happening on the other side. Sorry, I've just got the wrong one. Okay, this is the one and this is the other one. My apologies. So two symmetry as we have cut on left side and right side and fixing on the bottom. Okay, now what I have in this study is a dead load of 6672.5 Newton on top lead, and my load is recalled from my thermal stress. Okay, so this thermal stress will recall this loading as temperature variation from thermal, as the heat fluxes were assigned to that one. So again, emphasizing on very important fact here, thermal analysis, you get the temperature distribution. And thermal stress studies is basically linear static or nonlinear static, will uses that temperature to look at the stress strain, means this different temperature at different location, different expansion, and that cause stress strain into your model. Alrighty guys, so applying the correct, let's say, mesh controls, and we basically have to solve this model and looking at different, let's say, locations and the magnitude of the stress, displacement, and strain, and see how it is, let's say, distributed. Okay, now this is getting solved, and what I will look at the end is my values of the stress. Okay, so unfortunately I have lost the, let's say, result file, and needs to be quickly run again. In your linear static study, it's more than important that you are providing the correct material information, such as elastic modulus and let's say Poisson ratio and yield strength in your material properties. And the link is always possible between your thermal stress study and thermal studies within load definition or studies property, and I will show it very quickly. So while it's getting solved, let's go and simply do the second thermal study, let's say thermal stress studies here, as I'm switching to the next one. And simply we have no heat flux, therefore there is no thermal study, and in this we just have the dead load applying. So a linear static study, well, we have no heat flux and we just have a dead load here. So this is the stress when you have no heat load, and in our thermal stress, when you have the heat load, the stresses are look like this. Well, basically we can see some let's say peaks on the bolt connection area. Well, we can understand the stress singularity is there, and it's not the main concern, and we know it is a numerical, let's say, fault or peaks or noise. Well, we can simply avoid it. But the other regions we might be interested is those regions, and that is a possibility to failure if the load is getting repeated. Now, what we have done up to this point, we have set up two thermal stress studies, one with the maximum heat load, which is connected to that thermal, and the other one is without any thermal loads, and it's not connected to anything because there is no thermal loads there. Now, it is again the time to make sure we have two more linear static studies. Well, the pressure fluctuations are considered. As you can see, this is the first study, and we have simply set the pressure of 3.3 megapascal to act inside the pressure vessel. Dead load is there, restraints are the same, material is the same, contact set are the same, and we have the bolt connection. With the same mesh control, we have solved this, and we found the stress values on this specific study. Well, we can see obviously, yes, these are the singularities. Well, we have the bolt connection. However, we can see something considerable here, and still it's less than the, let's say, yield strength. It's not showing us a failure, but this magnitude, as we are expecting, is something high here. Again, the question might be, if we are repeating this sort of pressure loading for 500,000 times, what would be the outcome? The next static pressure study is considering the pressure loading to be vacuum, and it's minus 0.66. Here it is, and the results are simply showing that much stress. Okay, so all of these studies, static pressure minimum, static pressure maximum, thermal stress with maximum thermal load, thermal stress without any thermal loads, all are showing no plastic deformation and stress values less than yield point. Now it's the time to set up a fatigue study here. Okay? Basically, fatigue study can be set from your new study section and be going to fatigue, and you simply can see the options. Constant amplitude event. As I said, this is our main concern for today, but you can have a variable amplitude history data. Well, that would be an upcoming, let's say, webinar about how we can set up. And then you can have a harmonic fatigue of sinusoidal loading, and we can have a random vibration fatigue or random vibration studies at the same time. Well, the main concern is here, and simply be clicking OK, and this is a new study I have created. All right, the first thing we have to do is simply create an event, or let's say link our fatigue study to the values of stress conducted from individual linear static studies and thermal stress studies. Well, right click on here, adding an event. You can say what sort of loading history. For example, we would like to have to 2 million. And well, we know loading thermal is 0, nothing, and then it is maximum. Therefore, it is a zero-based loading. The first loading is coming from thermal stress, and then the second one is coming from the other one. Since we have no, let's say the interaction is no interaction, that would be enough. And 2 million cycle zero base, have maximum thermal stress, and then have nothing. Simple as that. We can click OK, and you have created your first event. Second event is referring to a loading ratio of minus 0.66 divided by 3.3. That is the loading ratio of minus 0.2. So simply I'm putting minus 0.2, and the cycle, number of cycle is 500,000. The studies are coming from static pressure and the second study of here. Okay, so static pressure, and simply the loading ratio from that static pressure should go up and down or fluctuate by the factor of minus 0.2 for 500 times cycle. Clicking OK, and I have two events. Now the next thing we have to do before we going anywhere else, you can see you have your material and the parts are listed, and simply I have to look at my fatigue data. Well, this is where we have introduced everything. First of all, you can define your fatigue data by entering N, number of cycles and alternating stress, and tell the stress ratio, which is the cycle as fully reversed here, as you can see, -1. It is interpolating by log data, and I can have up to 10 curves with a different, let's say, alternating stress or mean stress range, but I've just entered one. The alternative, let's say, solution, as we haven't, let's say, introduced, if it's an appropriate material, which our case is not, you can derive it from elastic modulus, either authentic steel curves or carbon steel curves. Then automatically your fatigue curve or SN curve will be produced. The software will get the elastic modulus of this material divided by its default value for this carbon steel, multiplied by the values of, let's say, alternating stress for this material, and provide you the alternation stress for your fatigue data. All right, so if you have a look to my first fatigue study, well, you can see the same thing. I have two events, event 1, and it's simply talking about zero base 2 million cycle of thermal stress, having full thermal load and 0. And I do have the event 2, which is talking about loading ratio of minus 0.2. Well, my pressure is simply varying from minus values of stress of minus 0.66 and plus 3.3 megapascal. With those events, correct values of SN curves, I can look at the result of the damage. Well, you can see there are some places where we have 100% damage, and we can definitely comment that since the stresses are singular at there, those values are not we are considering, and we can simply ignore it. That is because of the, let's say, bolt connection and the axial forces we have there. But one very considerable, let's say, area, and it's not singularity, is what we have here, and we can go and probe the value. And it is showing us 58% of damage after that many cycles. Means your thermal loads been varied 2 million times, your pressure load been varied by 500,000 times, and this is showing us a failure. 58% of the life is gone at that site. Whether it is something we have to consider and say, yeah, I have to go and change my design, or this is something which is, let's say, acceptable, and you're providing this instruction after having that much time or that much loading cycle, you have to go for a maintenance, replace this part, and etc. Okay, guys? We will go through this, let's say, damage plot and what does it mean more into detail in a slide. But before doing that, I would like to show you one thing more here, which is the properties of study. You can see those events, means variation of pressure and thermal stress, are random interaction. And simply, we have pickup. Let's say the peak cycles of stress from each studies, and the study simply provided our damage here. Mean stress correction is 0 here, and simply computing alternative stress is based on stress intensity, not equivalent or one misses or absolute principle. So you have the option to say my alternating stress should be read from the values of stress intensity, equivalent stress, or maximal absolute. These are all something that you can simply adjust. In my second fatigue study, guys, with the dead load acting here, what I've said in my events are simply 2 million cycle of find cycle peaks, means we have interactive, let's say, events, peak cycles here, and it is calling thermal stress 0 and thermal stress maximum. Similarly, it got pressure stress 0, or let's say minus 0.66, or static pressure 3.3 megapascal stress values there, and find cycle peaks. It is combining those ones, and simply in our fatigue study, you can see there is a random interaction between those events, and we still not using the mean stress, let's say, interactions. Now we can see we are predicting the same pattern with the different values as we just use all these events acting together at the same time. And if I go and probe this one, we are expecting less of 15% damage here. Or even I can go and modify my plot on a chart option to show the maximum here, show the minimum here, and also now going back to probe on somewhere in this area. So let's say around 16%. Here we have the damage. Cycle peaks or having all the alternating stress, well, definitely we are expecting different result, as the first one was considering all the range of stress and its fluctuation, but this one is simply getting the peaks and combining them. Okay? Now, the next thing I would like to show you before we finishing this one is here, and let's get back to our slide. The damage plot is basically showing us how much of the let's say life of the structure is being consumed. But one very important thing is the linear damage rule is getting used in a simple form when you are specifying fatigue events which are not interacting. And then it would be a ASME code to, let's say, combining the event peaks. If you are selecting, they have to, let's say, interact with each other. So coming as a solo or separate, or combining with the ASME code for combining the peak. But one very important thing is the linear interaction between those, let's say, cycles and the magnitudes. The minor role is basically using the first concept of SN curves indicate that it takes N1 cycles at alternating stress of S1 to cause the fatigue failure. Now, the minor role state that each cycle will cause a damage factor of D1 that consumes 1 over N1 life of the structure. Therefore, if your structure is subject to N1 cycle at S1 and N2 cycles at S2, means different values of alternating stress, then the total damage is the addition of damage 1 and damage 2. That is a linear combination of damage caused by different values of alternating stress. You can have a selection, your events, to have simply coming after each other and have no interact, or the cycle peaks to be interact in your setting. Alrighty guys, so that is the wrap up of our introduction really into fatigue studies. Well, we have reviewed the constant amplitude events and definition of SN curves, interpolation methods, and also we introduce how we set up. What is very important to understand is always we have different linear static studies, or let's say non-linear static studies, and recently in 2016 even dynamic studies as solo events, and in fatigue studies we are simply calling them either by saying it is a ratio of that load or cycle peaks of these loads, and then apply to our model and get to look at the damage factor and how much life is simply remain from the structure. All this said here is a part of SolidWorks simulation standard. Well, if you are having your base CAD model module, then you can add SolidWorks simulation standard, which you will be enabled to do any linear static studies on your part or assembly, doing time-based rigid dynamic motion studies, do fatigue studies, and let's say having a trend tracker. Just letting you know, if you have SolidWorks Simulation Professional, which is an upgrade to your SolidWorks, let's say, simulation, you will get all this option, and you are able to do thermal studies, frequency studies, and etc., as you can see in this box. Therefore, if you are considering any fatigue study like what I've done, considering thermal loads, SolidWorks Simulation Professional is required, as you have to know your thermal distribution. Okay? And the third level of SolidWorks Simulation is considering SolidWorks Simulation Premium, where you are able to do linear dynamic studies, non-linear static and dynamic studies, and you are considering composites. Again, I'm repeating, 2016 will consider linear dynamic studies to be added to your fatigue studies, which was not an option, and now it's pretty advanced, and you can have dynamic studies and their effect on the fatigue at the same time. Alrighty guys, just again as a reminder, we have the training session of Essential in let's say December. 3 days for Essential. Well, you are learning a lot on here, and also Professional, which is a specific application in SolidWorks. Please contact John Belsham if you are interested on that one. And if you have further commercial discussion, you can always contact John Belsham. And if you have any technical, let's say, question, I'm more than happy to take your, let's say, question offline. Please contact me at svandiar.kuhi@intercad.com.au, and we're definitely getting back to you by a phone, email, or even sharing screen. Thanks everybody for attending the, let's say, session. We hope to see you very soon with the advanced fatigue session as well. Thank you so much. Bye.